Hi guys, my name's Lauren Smith. I'm a 625-point student and I'll be taking you through to 2021's higher level question 9. It is a typical long question worth 56 marks and is all about the topic of heat. So, let's go. So here is the first look at our heat question, question 9, and it's broken down into roughly 4 parts. The first about specific heat capacity. The next, a calculations question about this said picnic box up here, and we're asked to find the final temperature inside the box when we put an ice pack into it. The next part is this little part down here where we're going to look at the heat bump. And our final part will be all about how heat travels through water with this famous experiment down here where we're going to test whether or not water makes a good conducting material of heat. Okay, so in part 1 we're asked what is meant by specific heat capacity. Now, the verbal definition is as follows, that specific heat capacity of a substance is the heat energy needed to change the temperature of 1 kilogram of the substance. Now, this little blurb here will get you your first 3 marks, and your next 3 marks is given by saying that the temperature needs to change by 1 Kelvin, giving you 6 marks in total. Now, if you're more mathematically inclined like myself, fear not, because you can also have a pure mathematical definition to get your full 6 marks. And for that, we're going to need to look at the formula and tables book. Before I continue on with part 1, I just want to draw your attention to page 58, the formula and tables book, looking at the formula of the energy needed to change temperature, which will include our specific heat capacity. Now, just stating this formula, or just writing it down here, will get you 3 marks. So even if you've written down the full verbal definition, I'd always put down every single formula that I'd find relevant to a question, because undoubtedly you're going to pick up marks somewhere, and if you're just copying it from the formula and tables book, they're practically giving you the marks. So that would be my biggest tip throughout the whole physics exam. So automatically, just not even learning anything off, we've already got half of our marks for this part of our question. And to get the other 3 marks, you simply have to notate it. You need to know what the variables actually mean. And you can do that by using arrows or doing a little table like I have up here. In part 2, we are asked, why does the high specific latent heat of fusion of ice make it a good coolant? And the answer is as follows. This quality makes ice a good coolant as the ice can take in a lot of energy as it melts. The definition of specific latent heat is the amount of energy needed to melt or freeze 1 kilogram of the substance, ice in our case, at its melting point. So therefore, ice has the capacity to take in a lot of energy before it changes state to a liquid. You'll get 3 marks for stating that the ice can take in a lot of energy, and another 3 marks for explaining that it can take in a lot of energy as it melts. As it melts being the key phrase here. In part 3, we are to suggest 2 reasons why the walls of the picnic box are made from hollow plastic rather than solid plastic. It's pretty evident that an advantage would be that the box is lighter to carry. There's less plastic. It's going to be lighter. And it's pretty clear that the box will have a lower environmental impact as it is overall made from less plastic. The box itself would be a better insulator. If the walls of the picnic box are hollow in contrast to a solid plastic picnic box, they will be filled by air, which is a gas, instead of a solid material. Since air is a poorer conductor of heat than plastic, the box is a better insulator by comparison. The box would also have a lower heat capacity, which is an advantage in this case, as there is a lower amount of heat energy stored in the walls of the box when it is at a given temperature if there is air filled in the cavities of the box. There are 4 accepted answers in the marking scheme. You need 2 of them to get your full marks. Each correct answer will get you 3 marks each. Even though it says to suggest 2 reasons, I'd always give down as many reasons as possible, as many as you can think of, because you never know, you can pick up marks along the way. Before moving on to part 4, we're given a little blurb of information up here. So we're told that a picnic box contains food items with an initial temperature of 10.5 degrees Celsius, and the heat capacity of the food is 17.8 kilojoules per Kelvin. Now, the fact that it says heat capacity instead of specific heat capacity is extremely important, and you must make note of this. That's why it's important to highlight all your keywords as you go through the information of the question. So we have also an ice pack, and it contains 250 grams of ice, and it was taken from a freezer. And this freezer was held at a temperature of minus 18 degrees Celsius, and this would also be the temperature of the ice. So this was placed in the picnic box, and we are told that the temperature of the ice increases and it melts, which is a very important concept because it's going to change state. So we're going to have to take this into account into our calculation. And we're also told that the temperature of the food decreases. And we're asked to calculate the final temperature inside the picnic box when its contents have reached thermal equilibrium. Now, thermal equilibrium is when the system gets to a point where the temperature is constant throughout the system. So there is no change in temperature of the food or the ice. It gets to a point in time where it is all the same temperature, which will be key in answering this question. Before I start answering part 4, I want to draw your attention to page 58 of the Formula and Tables book, where we'll be looking at the energy needed to change state formula, and also both of the formulae for the energy needed to change temperature. You're going to need both of these. Alright, so we're going on to part 4, and I have listed all of the known variables and the formulas we will need for this calculation. Just moving on to the formulas first, because you do pick up marks here. If you list either this formula, the first formula, or the third formula here that I have, you will get your first 3 marks. If you mention the second formula that I have here, you will get another 3 marks. So already you've picked up 6 marks without even calculating absolutely anything, and that would be my biggest tip in the exam. In any physics calculations question, look through the Formula and Tables book, or if you've learned all your formulas off, if you have fair play, put down any formula which you think is relevant for the question, because more than likely you're going to pick up marks. So some of the known variables need to be converted into SI units. The first one I'm going to look at is the heat capacity of food. Now it's in kilojoules per Kelvin, and we're going to need it in joules per Kelvin. So what we're going to do is we're going to multiply this value by 1,000 to get 17,800 joules per Kelvin for the heat capacity of the food. Now notice that we have 2 specific heat capacities for the 2 phase states concerning the same matter. What do I mean by phase states? I mean that it's in a liquid form, the water is, and we have a solid form that the same matter is. So notice that we have 2 specific heat capacities for the 2 different phase states concerning the same matter. We have the phase state of ice, the solid state for water, or for the H2O molecule, and we also have the phase state for the liquid form of water. And we're going to need both of these in our calculations. Now remember that specific heat capacity is different from heat capacity, which we saw up here for the heat capacity of food. Next, we're going to look at the mass of the ice. Now it's in grams, and we need to convert it into kilograms. So what we're going to do is we're going to divide 250 grams by 1,000 to get 0.250 kilograms. And we have the initial temperature of the food, and that's 10.5 degrees Celsius, and we have the initial temperature of the ice to be minus 18 degrees Celsius. Now we have it in degrees Celsius, but there is no need to change into Kelvin, as we will be looking at the difference in temperature of the initial and final states of the substances in the system. Okay? And because there is a constant difference between Kelvin and Celsius values, the difference in temperature of the initial and final states will be the same whether you're going to be measuring it in Kelvin or Celsius. You can still convert it into Kelvin, but it will just waste your time a little bit, and that's what we want to avoid. Okay, so we're going to be looking at the heat gained and the heat lost by the ice and the food, respectively. Now, the heat gained by a substance is given by the temperature change, in that we're going to subtract the initial temperature value from the final temperature value. So the final value for ice is going to be 0 degrees. And this is just before the ice turns into water through that state conversion. Now we're going to minus the initial temperature of the ice, which was minus 18 degrees Celsius. And the difference will be 18 Kelvin. Remember that remark. It could be a difference of 18 degrees Celsius, but again, like I said before, it doesn't really matter because we're looking at the difference in temperature. Now, the same can be done for the water. The final temperature of the water is going to be the final temperature of the system, which is what we're looking for. So I'm going to call that theta, and that we need to take away from the initial temperature of the water, which is 0. And that comes directly from this one up here. Okay, so the total temperature difference of the water is just going to be theta Kelvin. Now for the heat loss, this equation is reversed. So we're going to take the final temperature value away from the initial temperature value. So the total temperature change in the food will be the initial value, which was 10.5, take away the final value of the food. It's going to decrease in temperature. And that is the final temperature value of the system. Okay, so putting this all, we're going to have to put this into context in the form of our equation. And so we're going to have to put this all into our equation. But what equation will that be? The principle behind this whole heat transfer setup is that the heat gained by the ice must equal the heat lost by the food. And we're going to assume that there's no heat loss to the surroundings. It's just going to be contained in that box. So looking at the heat lost by the food first, that is given by the formula here, as we looked at on one of the previous slides. Now it is important that we use the heat capacity formula because we're not given the mass of the food, but we're given the heat capacity only. So this is the amount of heat energy lost by the food is governed by this formula. Now looking at the heat gained by the ice, we have 3 terms in the left side of our equation. The first term is going to explain the energy needed to convert from the ice from minus 18 degrees up to that 0 degrees point. So that's the energy needed there. Now the next step is the third term, I'm just going to skip to that, and it's the energy needed to change the ice from solid ice to liquid water. So it's changing state. That's the amount of energy needed to change state. And in the middle here, we have our third and final term. It's going to be the final phase that the water ice is going to go through, and it's going to correspond to the amount of energy needed to change the temperature of the water from 0 degrees to the final temperature of the system. Okay, so we can sub in all of our values in here to get this equation here. Notice that here L is equal to 3.3 times 10 to the power of 5, and that is given at the end of our question. And for this substitution, you will get 3 marks for the right hand side and also 3 marks for the left hand side, having all the correct figures. So all we have to do now is to calculate each of these values here. And for that, we're going to use the calculator. Okay, so let's start off with the left hand side because that's where most of our numerical figures will come from. So for our first value, we have 0.25 times 2100 times 18. I'd always use brackets instead of multiplication symbols because in some calculations you're going to be using scientific notation, and it just ensures that the calculator knows what you are calculating. So there we have 9450. That's our first term, plus 0.25 times 4180, and that's times theta. This is the coefficient in front of theta. That's 1045. So we have 1045 theta here, and we're going to add that to 0.25 times 3.3 times 10 to the power of 5. Again, this is why brackets are more helpful than multiplication symbols, like this one here. And that gives us 82,500. And now let's look at the right-hand side. We need to multiply 17,800 by 10.5, which is equal to 186,900 minus 17,800 theta. Okay. So I'm just going to rearrange this formula so we have thetas on the left and all of our constants on the right. So we're getting that 17,000. We have our 2 theta terms on the left. And on the right hand side we have 94,950, and that's by putting all of our constants to the right hand side. Adding both of these theta values together, we're going to get 8,845 theta is equal to 94,950. Now we just have to divide across by 18,845, and we're going to get our value for theta. Okay, so theta is equal to 94950 divided by 18,845. Let's put this into the calculator. So we have 94950 over 18,845. That's equal to, we're going to give this fraction value, but it's best to convert it always into decimals, especially when dealing with temperature. And I've given my final answer to 2 decimal places. I've rounded it to 5.04 degrees Celsius. Not forgetting your units, and we get our final 3 marks here. Okay, so in the next part of this section of our question, we are told that freezers and refrigerators operate by use of a heat pump. And in part 5, we're asked to draw a labeled diagram. Be careful of the word labeled. You will lose marks if your diagram is not labeled, of a heat pump. So here's my diagram here. I know it's quite detailed and I put in a lot of labels to labor the point that you always have to label your diagram. You will lose marks. And also the labels can help you piece together what's actually going on in the exam if you have that little bit of exam panic or just stress. It's easier to forget things. Understandable, I've been there. Now, places where you will get marks. You will get 3 marks for showing where the compressor is, and for also having an expansion valve, you'll get another 3 marks. And your next 3 marks will go for the correct arrangement of the liquid or the vapor, i.e. that heat is given off over here, and that's where our vapor is. It's given out by the vapor, and that we have low pressure vapor up here and low pressure liquid down here after being put through the expansion valve. And as it's going through the inside of the fridge, it's picking up heat, all this latent heat, which is vaporizing the liquid we see down here. And also showing the arrows, i.e. the direction of the liquid or the vapor as it's going around, will also help you get those last 3 marks. I'm going to put up here. So a total of 9 marks for this diagram. Now moving on to part 6, we're asked to explain how a heat pump works. Okay, so a heat pump transfers energy from a cooler region to a warmer one. This is the main reason why we use heat pumps in fridges and freezers. And this is done by using a liquid, which we saw in the diagram, and that's pumped around a closed circuit again, like we saw in the diagram. Now, before I get on to the rest of the explanation, I have to say that the liquid itself has a high specific latent heat, which means that it can take in a lot of heat energy before it changes temperature, which is a very good quality for the liquid to have. And also, it needs to have a low boiling point, so it doesn't require too much effort to vaporize as it goes through the back of the fridge or the freezer, collecting that heat. Now, to get your first 3 marks, you have to explain that at the expansion valve, the pressure will drop, and therefore the liquid vaporizes as it takes in its latent heat from the inside of the fridge, cooling the inside of the fridge. Specifically stating that the liquid vaporizes as it takes in heat will get you your first 3 marks. Your next 3 marks will be attained by saying that at the compressor, the vapor's pressure increases, turning back into a liquid, giving out its latent heat in the process. The heat is therefore given off in the surroundings, which we've shown in the diagram in part 5. This will get you 3 marks. And I just put in at the end that the cycle repeats itself, which it does, which is an important part of the heat pump. It just keeps going and going and going. Now, my tip would be for if you're going to have like long-winded explanations like this one, which is required for the heat pump, break up this explanation into small paragraphs to explain each stage of the cycle, like I've done here and here. Looking at the last section of our question, we are told that a student uses the apparatus shown, which is this apparatus down here, to investigate how heat travels through water. So this will cover our answers for parts 7 and parts 8. Okay, so this experimental setup is as follows. We have a tilted test tube here filled with water, and at the bottom of the test tube we have an ice cube, and that's been held down by a metal weight. The metal weight is in place because we want the ice cube to stay at the bottom of the test tube. At the top of the test tube, heat is being applied, as you can see in the form of bubbles up here, to the water at the top of the test tube, and we are to observe what happens in particular to the ice cube. In part 7, we're asked what observations did the student make. As we know from the experiment, if we watched it being carried out, the ice cube did not melt, which in principle is equivalent to saying that the bottom of the tube stayed cold or that heat did not transfer to the bottom of the tube. Therefore, both of these answers are acceptable and either one shall get you 4 marks. Now, why did the heat which was applied to the water at the top of the tube have no effect on the ice cube? Well, the answer to this question will be given in part 8. Part 8. What conclusion could the student have made? Conclusions are very important in physics experiments, so make sure to learn them all for all your demonstrations and your mandatory experiments. This is the reason why we do experiments in the first place. The only acceptable answer is that water is in fact a poor conductor of heat. And that's what we were trying to prove in this experiment. And this explanation will get you 4 marks, okay?